Well, hello everyone, and good morning or good afternoon or good evening, depending on where in the world you are at the moment. I'm hoping that everyone can hear me. We had a rehearsal of this yesterday, and we seem to be all right. I'd like to welcome you today to this webinar on an introduction to vibration and dynamics. I suppose really the reason for writing this webinar in the first place, and the paper associated with it, which you can request at the end if you like, was because I struggled with dynamics at university because it was taught very mathematically, and very often the concepts that came out of it were introduced mathematically, and I tended to get a bit lost. It's true the maths is very elegant and very beautiful really if you're into that sort of thing, but it can be quite confusing. So what I want to do here is to introduce dynamics and vibration without the maths, but you will see that I've got some bits in there just so that hopefully you can relate them back to what you did at university. So let's get straight into it and just have a look at some things. In particular, let's have a look at what resonance and vibration really is. So you've got to bear in mind that every material and every structure in the world, it vibrates at a preferred natural frequency. If we look at a bridge and it looks like it's standing still, we have to realize it still is vibrating. It's just the amplitude of the vibrations are very low and we may not be able to feel it, but it is still there. It's not just structures, it's pretty much everything that's got a mass will vibrate. So even down at a molecular level, for instance, in water, then we find that there's vibration. So if we look at water molecules, which are oxygen and hydrogen atoms, then together those molecules have a mass, and they're held together with hydrogen bonds. So they have a resonant frequency, they want to vibrate, and as we'll see later, we can work that out from an equation of the stiffness, in this case of the hydrogen bond, K, divided by the mass of the molecule. Now, we can use vibration to our own benefits. So the nice thing about vibration is if you introduce just a small amount of energy at that natural frequency, you'll get a huge vibration response. And we use this in water to our own benefits. We introduce vibration near to the natural frequency. That excites the movement of the molecules, which creates friction, and that creates heat. And that's really the principle behind microwave ovens. Okay, technically we don't actually excite the molecules at their natural frequency, because if we did that, then we'd heat the outside of our joint of meat very, very quickly, and the inside would still be cold. So actually, we choose a frequency which is a compromise. And that frequency is enough to add significant vibration in there because it's close to resonance without overcooking the outside and missing the inside. And again, if you're interested in finding out more about this sort of thing, look online, and also look up, while you're at it, induction kitchen hobs or induction furnaces, because these sorts of things for doing thermomechanical fatigue testing also use a similar principle, rather than with water, with ferrous ions. So the key thing that we get out of it in resonance is if you add a small amount of energy at the right frequency, you get a lot of response. Of course, we're more interested, I think, in structures. And if we look at this very simple structure here, okay, forget the blades and things like that for a minute because they're dynamically very complicated. But if we concentrate on the tower of this wind turbine, we see that actually it's pretty much a single degree of freedom system. It's a tower with a stiffness, and it's got a big mass, the nacelle, on the top. And we can approximate that to that single degree of freedom, a bit like a molecule of water and a hydrogen bond. And again, we can work out its natural frequency as root K over M, just as we did before. Just as we saw with the water, if we introduce a small amount of energy near its natural frequency, that gives us a huge response, and this time, rather than being beneficial to us, it can create possible failures. And when we talk about dynamic failures, yes, we're talking about ultimate limit state failure, the bit where it shakes itself to pieces and collapses, but we also have to consider what we call the serviceability limit state as well. This isn't where we've wrecked the structure, it's where we've introduced significant movement in there, but it's actually limiting the structure's ability to operate. And with things like wind turbines, these can be aeroelastic type problems, or it could just be excessive deflection, or it could be an excessive amount of damage. So wind turbines, for example, will switch off with wind speeds greater than around about 45 miles an hour in order to save themselves. Yes, they could carry on, they wouldn't collapse, but the damage is accumulating too quickly. So this wind turbine tower is a very simple example, and we could just use a pocket calculator to work it out. Of course, not all structures are quite so simple. If we look at, say, a multi-story tower block, then in this case we've got what we call a multi-degree of freedom system. Effectively, we've got now columns which link floors. So each of the floors have a mass, and the columns are probably similar stiffness. And now if we start to shake it, we find that there's several modes to the way this building wants to vibrate. So the first mode is just the swaying mode, but if I increase the frequency, for example in an earthquake, I may at a certain frequency get away from mode 1 and into mode 2. And now you'll notice that the first floor and the fourth floor stay still, but the second and the third are bouncing around. And if I increase the frequency even more, we now find second and fourth floor stay fairly still, but the first and the third are moving around out of phase with each other. And if I want to increase it even higher, we now find that all the floors are moving out of phase with one another. So here, it's not a simple equation that we can do on a pocket calculator, it's a more complex situation. And the big problem is that if we excite any of these natural frequencies, we'll get that huge response, which could lead to a possible failure. So now it's not just a matter of avoiding one key frequency, we're now having to avoid 4 key frequencies. So what we've seen here is that if we have a more complex structure, like this block of flats, then it has separate mode shapes that we vibrate, and each mode shape has a separate natural frequency. Now again, the building is relatively simple. Many mechanical engineering structures, and civil engineering structures in this case, use distributed masses. So rather than having big lumps of floor and concrete floors at each point, the masses are distributed, and so is the stiffness. So if we look at the Tacoma Narrows suspension bridge, then the bridge deck itself is the distributed mass. It's not all in one lump, it's distributed along it. And if we look at the stiffness is via the deck and the catenary cables. Again, the stiffness varies too. We also see that this isn't a simple one-dimensional structure, it's a three-dimensional structure. So not only do we get the bending modes, but as you see from the photographs, we also end up with torsion modes. So now there are many modes of vibration, each with their own natural frequency, and if we start to excite the structure near those natural frequencies, that leads to a huge response and the possible failure of it. So in conclusion then, every structure, it wants to vibrate. It really does want to resonate. That's its natural state. If it looks calm, it's simply because the amplitude is too low. Deep inside it, if it's above absolute zero in temperature, it is vibrating. The resonant frequency that it vibrates at really depends on the ratio of the mass and the stiffness. We see that simple equation there as root k over m. Essentially what's happening is mass gives it inertia, and the spring stiffness, the two act together and they reinforce one another, as we see later, by acting in phase. So we can actually start to excite something to catastrophic collapse. It only takes a small amount of energy input at that resonant frequency to create a very high response. That's because the energy you're doing is additive to its own inertia that's going in there as well. And of course, as we've seen, complicated structures can have more than one resonant mode. Each resonant mode has its own frequency. So the task of engineering then is we've got to avoid failure. So that means avoiding excess displacement, or avoiding excessive stresses due to resonance, or avoiding excessive fatigue accumulation rates. And we can tackle these in several ways. Firstly, we could detune the structural resonance. So if we know the loading frequencies, we could tune a structure so that it doesn't have a natural frequency which coincides with peak loading frequencies. It's very commonly done on aircraft and also on power generation, where we deliberately detune the structure to avoid certain rotation frequencies and harmonics of that. Another approach, because detuning structures is very complicated, we could in many cases isolate the structure. So ISO mounts are determined so that they can actually isolate key frequencies out of the response so that it never gets transmitted from the mounting structure to our component. Or thirdly, if we can't do any of those, we need to design our structure to dissipate that resonant energy through damping. So in this webinar, what I want to do is to go through these three parts. I know originally I said it were two, but I've split part one into two parts to make it clearer. So part one, we're going to look just at an introduction to structural dynamics. We're looking at the response of structures to vibration. In part two, then we're going to have a look at how do we characterize loading. So part one is all to do with the structural response. Part two is all due to the loading vibration. And then at the end of that, we'll see how we can bring the two together to start to predict the response. And in this case, we'll use our windmill. And then in part three, we'll go on to cover more complex ones. So part one and two, we're really considering single degree of freedom systems. But in part three, we'll expand that to cover all the things that we need on multi-degree of freedom systems. So in part one then, what we're going to start with is to look at the dynamic equilibrium and natural frequency. And there's going to be a little bit of maths in here, but it's going to be noddy maths. It's going to be fairly simple. Don't want the maths to confuse the basic principles of what we're doing, but hopefully it should still tie it into what you learned at university. Once we've learned about natural frequency, we're going to start to talk about frequency response functions. And this will bring us on to the effect of damping, and what we mean by the term quasi-static response, and also we're going to introduce the effect of linear and non-linear structures. Okay then, so first of all then, we're going to consider this windmill, and as we said, the windmill could be considered, if you look at the tower, as a simple single degree of freedom system. And when we talk about dynamic equilibrium, we usually talk about this equation. Now I'm going to bring this equation in because it's a nice pretty equation and it sums up everything quite nicely. So let's have a look at that equation and see what it actually means. So on the right we see that we've got a forcing function. The force changes with time. It's a dynamic load. And on the left of that equation we can see how the structure responds to that force. And first of all, we see that a structure responds through spring resistance. So this is static forces. So if the structure is not moving and I've got no load, I've got a constant load, for example, just pushing the tower over like this, we know that that tower is going to exert an equal and opposite reaction. And that's equal to the stiffness of the tower multiplied by its displacement. And here it's a simple cantilever, so it can work that out. So if it was a static force, then there is a static resistance, which is known as stiffness or spring resistance. Now we also know that if we've got a mass on the tower, then we've got an inertial resistance. So this is all down to Newton's second law of motion, and this is saying that force is mass times acceleration. So we've got a mass, we're accelerating it by a force, so if it's moving with an acceleration, that is also going to give us a force. And thirdly, there's actually a force that's related to the speed at which it's moving. We call this damping. And really, this is the force that's required to move the body through the viscous fluid. In this case, our wind turbine, it's the force required to push the turbine against the wind. And that's quite significant force because obviously wind turbines are designed to harness wind energy, so they're very effective with movement through backwards and forwards. Of course, damping isn't just limited to viscous fluids and things. We also get damping through slippage in things like riveted or bolted joints. We also get natural damping in materials as they absorb energy. There's damping in rubbers. And there are various types of damping, which we'll not go into here, but we've got hysteretic type damping and friction damping. Some damping actually applies not so much to the velocity and the speed, but sometimes actually to the amount of motion as well. We call it damping because really what it's doing is it's taking out energy in the system. But generally, traditionally, damping is related to a speed term. So let's have a look now at how these three interact. So first of all, if I have a wind turbine and I give it a good flick or belt it with a hammer at the top, then it will start to vibrate, a bit like a ruler on a desk. And if I look at the motion, the displacement at the top of that wind turbine, we see it follows a sinusoidal wave. If we look at that, we can see now that I've drawn it as a cosine wave here. It's got amplitude of A. It's going with a frequency of omega here in radians per second. And first of all, at point 1, we can see when the turbine, when I pulled the tower right over, I've now got my maximum spring force. It's wanting to pull it back to the middle. So when I let it go, that spring force is going to pull the turbine back to the middle, where the force becomes 0 now. It will then overshoot through its own inertia, momentum and go to point 3, where it's now got maximum spring force again, but in the other direction, which is going to pull it back. Of course, if we look at speed, we can see this is the momentum really of it, the speed. So when the turbine tower is at point 2, so it's now gone from full extreme at 1 through 2, even though there's no stiffness force now, that's been dominated by the mass and its own velocity. So that's the momentum that's pushing it on. As it pushes it through point 2 to point 3, the stiffness is now building up to oppose that force until at point 3, the two are in equilibrium, and then the stiffness overwhelms it and it starts to bring it back again. So here we can actually see that it's a sine wave. And all we've done is simply differentiate the displacement, and that's giving us the speed. Of course, there's also acceleration. So the acceleration is the inertia of the system. And again, if we were to just differentiate the speed, you'll see that we get the acceleration of the top of the wind turbine. So again, this is now out of phase with the displacement. So when we're at point 1, the maximum acceleration is actually slowing down the turbine as it's moving to the right, and then it's accelerating it to the left again. So we can start to see this acceleration coming in, or the inertia. Okay, we'll go a bit beyond words now. We'll put a few maths in. So we've got this differential equation. But let's not worry about that too much, because we've actually got a partial solution to this. So we know from there what the acceleration term is, x double dot, and we know its displacement. So we can just substitute those two into that equation, and if we simplify, we get this very simple equation down there at the bottom. Now, if we want to find the natural frequency, again, it's very easy, because we saw earlier that at natural frequency, you don't need an applied force, so the force can be 0. So if the force Ft is 0, it means either A cos omega t must be 0, or minus m omega squared plus k must be 0. And if we simply rearrange that, that gives us that equation that we nicely see, which is the natural frequency, root k over m. Okay, so a little bit of maths, but hopefully it's quite clear where it all comes from. Of course, we don't usually, as engineers, use radians per second. Radians per second are nice mathematically because the equations are simple. We tend to use hertz, or even natural periods. So that equation, root k over m, very often is converted into Hertz notation or into a period of time, which is just 1 over frequency. We tend to use periods where we've got very low frequencies, so things like wave motion in offshore structures. Rather than trying to do it in fractions of a hertz, we would tend to do it in terms of the period of the wave instead. Okay, so that's natural frequency then, and we've even put some maths in, and hopefully we can see it's a relatively simple concept. What's the frequency response function then that people talk about? Well, what this is it's very simply a case of trying to plot the maximum response of a structure at any particular frequency. So the easiest way to think of it is if we excite our wind turbine with a sine sweep, so it's the same amplitude but starts at a very low frequency and then gradually builds up frequency, we can look at how the wind turbine responds. And at the tower top, we first of all see that when the frequency is very low, it responds almost statically. So 0 hertz is just constant force, a constant wind speed. So we'll get a constant deflection. Then as we start to vary that sinusoidally, it'll start to grow, and at some point we hit that natural frequency where we get that exponential increase in response. And then if we blow through that and go further, then we'll find it dips down. So what the frequency response function is simply a graph that plots displacement or response with respect to excitation frequency. And if we look at this, we see very typically, I've done this as a normalized response, so the static one is 0 effectively. And as we build up, we can start to see how we get to the natural frequency there, where it becomes exponential, and then as it goes down, we move away from it and it reduces again. Let's go beyond words again. Again, the maths here that we're going to consider is very simple. We'll start off with the dynamic equilibrium equation. We'll look at the total force on the wind turbine, which we saw in the last slide, as a simple expression. And rather than setting force to 0, we're now going to excite it with an input force, just F cos omega t. So what we can now see is that the cos omega t's on the left and right cancel out, which again gives us this nice equation. And if I want to find the amplitude of the response A, I simply have to rearrange the equation, and what we see there is the frequency response function. The frequency response function is simply 1 over minus m omega squared plus k. Now this equation we usually split into 3 parts. At the very low frequencies, which are much lower than the natural frequency, then the component behaves what we call quasi-statically. In other words, the frequency of loading, it may be changing with time, but it's so much slower than the natural frequency that the natural frequency isn't really excited. And a lot of people have come up with a rule of thumb that says if the loading frequency is less than 1/3 of the natural frequency, let's just assume it's static. So we ignore the mass and inertia terms, we ignore the velocity terms, we just cope with the static terms. And at most, as we see from this graph here, for this wind turbine, we're probably going to be 10 to 12% out, which tends to be the same allowance as what we use for stress convergence in FE and many other things in engineering. So that's where the rule of thumb came from. Similarly, if we go way past the natural frequency, now we're exciting it with a force that's so fast, the structure never has chance to react to it. This is very similar to stones hitting your car. If you put an accelerometer and you flicked it, you'd very quickly go off the scale, the accelerometer. However, the duration of that little impulse, that stone hitting the accelerometer, is so low that actually it's not really reacted to it. So with very high frequencies, much higher than the natural frequency, the structure never has time to react to what's going on. So the response is very low. At this point, the response of the structure is governed by the inertia terms. the mass times the acceleration is what dominates it, and simply those short blasts of load just aren't long enough for it to make any reaction. Its own inertia stops it from moving. The bit that's the problem, of course, is that bit in the middle, the bit in the region of the natural frequency. And here what we see is the response is governed by damping. So let's have a look what's happening at the natural frequency. Well, basically, the external force now is in phase with the structure's own inertia. So when the structure is moving forward with its own inertia, we're pushing it to give it an additive force. So the two forces start to add together, and very often it goes out of control and it tends to infinity. So the speed is building up, the displacement's building up, and this is why damping starts to come in. So because the speed is building up so much, then damping, which reacts to speed, is also building up. So what we find here is that the damping starts to limit the motion around about those natural frequencies. So as I increase the damping, then that peaked curve starts to come down. And if I can introduce what we call critical damping levels, then at this point we introduce so much damping that it absorbs completely the energy that's causing the resonance. Now, I won't go through the proof, but we can calculate critical damping quite nicely. It's 2 times the square root of mass times stiffness. And we very often express damping as a ratio of critical damping. So it's usually the percentage of critical damping. And we do that because lots of structures, the damping value will all change dependent on the geometry of the structure, its size and everything else. But for certain types of structure, then the damping ratio tends to be fairly consistent. So we very often use a percentage of critical damping, a damping ratio, to express a generic damping term. You'll also see that the natural frequency reduces when you add damping. You can see that if you look at the natural frequency through that red dotted line, and then as we increase the damping to the purple line, you see that its natural frequency is now reduced. And when it goes to critical damping, then in theory, there is no natural frequency anymore. It's brought down to 0. What we do find, though, is if you want to do the maths, you'll find it follows this simple equation here. But what we find is that in most levels of engineering damping, it really doesn't change that much. So when we talk about 5% or even 10% damping, that won't make a huge change to the natural frequency. So in many cases, we do talk about the natural frequency as being the undamped one, because in most cases, there won't be much difference. The other thing that you may hear talked about a lot is the Q factor, or the dynamic amplification factor. This is, again, very easy to work out. It's just 1/2 times the damping ratio. And what Q is, you can see from the little graph there, is it tells you the dynamic amplification. So if you're loading it statically, the displacement is 1, so Q is 1. Now what this is saying is if, for example, you've got Q of 10, it's saying that the response at the natural frequency is 10 times greater than its static response. So this is a really nice figure to talk about, again, determined purely by damping, but it starts to say if you know the load that you've got, if you were to excite it at the natural frequency, it's giving you an idea of what the overload is going to be, the dynamic amplification, by resonating it. And finally, just before we leave this section, very often we talk about linear and non-linear systems, and these are very common in dynamics. And engineers have found wonderful ways of linearizing systems because non-linear dynamics are extremely interesting and in that read very complicated. So a lot of universities do a lot of work on this, and we start doing a lot more in general engineering. Generally, what we're looking at with nonlinear dynamics is it's very often in the displacement and the damping. So we can see here, on the left, for instance, this is a structure where when I increase the amplitude of the force, the resonant frequency is reducing. So in other words, the nonlinear effect here is effectively the stiffness is decreasing or is changing its natural frequency as the force increases. And conversely, if we look on the right, we see here as the force is increasing, the natural frequency is actually getting higher. So it appears to stiffen with increasing deflection. So these, again, are things that we can look at to see. And we'll see at the very last slide tools to enable you to see quite how the natural frequencies shift with respect to amplitude. Okay, so in that little section, what we've looked at is, first of all, we've looked at the equation of motion or dynamic equilibrium. We've solved it and we've found the natural frequency. We've solved the same equation a slightly different way to find its frequency response function. And from the frequency response function, we've looked at the effect that damping has at the natural frequency. We've separated that from quasi-static and inertia-driven responses. And we've also had a very quick look at what linear and non-linear structures look like. What we want to have a look at now is, now we see how structures respond to dynamics, how do we characterize the input loading to know whether we've got a problem? So remember what I said, one of the methods of avoiding failures in dynamics is to detune structures. But how do we know what the loading frequencies are to know whether we can detune it? And this is done by the power spectral density. So in this section I'm going to introduce the power spectral density, again with no maths, and we're going to look at how the power spectral density can be used with the frequency response function in order to estimate the output or the response of a structure. So first of all, what is the PSD? Well, you can think of a PSD as being a prism. It's a mathematical prism. So we all know that light is made up from different colours of light. So if we look at the sunlight that's coming to us, we know it's made up from a variation of colours from red all the way through to indigo. And they're mixed in different amplitudes. Each colour has a different frequency or wavelength, and we add them together to make up the colour that we see. And if we put a prism in our window, then it will separate those and tell us how much of each colour there is in it. And that's essentially what our PSD is doing. It's assuming that we're measuring vibration, and that vibration comprises of lots of different frequencies. And it's acting like a prism in order to separate the frequencies so we can see them more clearly, and we can see which frequencies are big and dominant and which ones may be smaller. So how does it work? Well, it's called the Fourier transform because it's based on the work of the original mathematician in France, Monsieur Fourier. And Monsieur Fourier in 1768 postulated that if you take any wave, and we tend to draw a square wave at universities because it's easy to characterize analytically. If we take any wave that repeats itself, we can decompose it into sine waves or sinusoidal waves. And of course, the bit we want to know is we want to work out what the amplitude and frequency of each of those are to see whether or not they're going to excite our structure or not. And as Monsieur Fourier said, if you add the waves back together again, you'll be able to recompose the original signal. So my first wave is a simple sine wave. If I now add it to the second wave, you can start to see just with two sine waves how they're starting to recreate the flat tops. And if I add the third one, it's getting closer to the original, and by the time I add just the fourth one, you can already start to see that square wave being built up. And if I add them all back together again, I would end up with a perfect representation of that square wave. So what we're doing here is a numerical prism. It's taking vibration and it's working out the amplitude and the frequency of those. Now we use a PSD for that. So this was developed in the 1940s, and it was originally pioneered by the electronics engineers, and they were doing the same as us. They wanted to look for noise in a circuit. The idea being if they knew the frequency of the noise and where it was originating from, they got a good chance of filtering it out or changing the components and getting rid of it completely. they were interested in finding the average amplitude of the noise at different frequencies, and they came up with a really neat way of doing it using just analog instruments. And this is really what the PSD is doing still today. So if we were to tap into that electric circuit and we were to measure the electrical power going through it, hence the name power spectral density, they're measuring electrical power, we get a time series coming out. What they did, in order to split the frequencies, is they simply passed it through a sweeping filter. So the filter changes with time. It starts off with a low frequency and the frequency changes. So at any particular frequency, you can actually take the input, filter it, and that gives us a signal as you see here. Now they're interested in finding the average amplitude, and if you try and find the average of this, you'll see that the negatives offset the positives. So the amplitude, the average, would just be 0. So they said, don't be not a problem with us. The mathematicians have addressed this for years. All we do is multiply the signal by itself and square it. That means everything is positive. So now we've got a wholly positive series. We can find out the average of that, and that gives us 1 point on the plot. Okay, it's not the average, it's the mean, it's the average of the square of the signal, so the mean squared. But hey, it's good enough. And as we move that filter through, you'll see that we start to plot how the mean squared changes with the frequency of the filter. And finally, the PSD was defined as the instantaneous amount of energy. So when it jumps from one level to the other in the cumulative plot, we see the amount of energy in that frequency band. So the PSD in this case is a density function. It's a histogram. You measure the area under the curve between two frequency points, and it tells you the mean squared energy that's driving the signal at that point. If we have a quick look, we can see here some sine waves and various waves. So this is the PSD of a sine wave. It's a single point in frequency, which coincides obviously with the frequency of the sine wave. If you measure the area under that spike, that gives you the mean squared amplitude of the sine wave. And really, if you just multiply that by 2 and square root it, that's going to give you an estimate of the actual amplitude. We can also see a narrowband process here. So a narrowband process is very easy to see in the PSD because it's only a narrow range of frequencies, and we can see that here. A broadband process, this is one that covers a wide range of frequencies, either by multiple spikes like this or one long big plateau. Again, it's hard to distinguish what frequencies there are in the time domain, but by looking at the PSD, it becomes very clear. And finally, here's a white noise process. This is where we excite all the frequencies with the same amount of vibration. It sounds a bit like the wind blowing through trees, and it's what we use usually as the starting point for vibration shaker tables. We start with white noise and we filter it to give us the characteristic that we're after. There are certain processes, like the wind turbine, where actually all we need is the amplitude and frequency. All waves really are made up of 3 things: amplitude, frequency, and phase. But many components, including the wind, engine vibrations, sea wave loading, things like that, the phase is actually purely random. So if we were to measure the loading, for example, on our wind turbine, then the time histories would be radically different from, say, one 15 seconds to the next 15 seconds. But if we look at the PSDs, they tend to be the same. What makes the time histories different is the phases are different. So the PSD, again, is a nice way of telling us what energy there is at each frequency. So what we've done here by looking at PSDs is we've just introduced that concept of a frequency domain. It breaks the signal down. So signals, we assume, consist of many sinusoidal waves. Each one has various amplitude, frequency, and phase. And we separate them, just like a prism does, so we can see the frequency and the amplitude. We've also seen that there are certain components, like the wind turbine over there, which phase is purely random anyway, so it doesn't really matter. The amplitude and the frequency is all that matters there. So can we use that then with our wind turbine example? Let's do a quick case study. here's my wind turbine, and if anyone wants the slides after this, get in touch with us, because I can send you the slides and also an accompanying paper which has a bit more of the maths in if you're interested. So I'm going to have a wind turbine here. It's got a mass of 38 tons at the top, a tower height of 40 meters. We're going to do a quick estimate of what the natural frequency is. We're then going to work out, based on a simple damping assumption, what dynamic amplification is, and we're also going to look at how the wind turbine will respond to turbulent wind gusts. And these numbers, by the way, are purely fictitious. They're all out of my head. They don't relate at all to the wind turbine that you see. So the first thing we need to do is, we know the mass, it's 38 tons. How about the stiffness? Well, it's a simple cantilever tower here. I'm going to assume that it's perfect encastre at the bottom, that there's no stiffness due to the foundation, it's infinitely stiff, and therefore I can make this simple assumption that the stiffness is just 3EI over L cubed. I'm going to assume that I've got a 2-meter diameter tower, and these turbines usually have a tapered tower, but this one I'm going to just assume for simplicity is constant section. It's 20 millimeters thick, 2 meters wide, and it's made of steel. So from here I can work out the second moment of area of the tower, and I can work out its stiffness. It's 586 kilonewtons per meter of displacement at the top. I can therefore work out its undamped natural frequency just by substituting into that simple equation. It's 0.625 Hertz. I could work out its damped natural frequency. Let's just assume, as we'll talk about damping later, let's assume it's 5%. So at 5% damping, it would actually make it just 0.624 Hertz. So hardly any change through damping in the natural frequency. And the dynamic amplification would be 10. So in this frequency response function, you can see there, if we were to excite it at its natural frequency, then the response would be 10 times greater than the static response would be under the same force. Of course, we've now got PSDs. So not only have we got the frequency response function in the top left, but I also can calculate the power spectral density of the wind load. And we've used a time history here of the load on the turbine, and I've fed that through GlyphWorks to work out its PSD. The nice thing here that we see is, if we look at the natural frequency, we find that we've managed to detune the wind turbine. It's not the best detuning that I could have done. If I put in a tapered tower, where it's stiffer at the bottom and less stiff at the top, I could have detuned it better. So the natural frequency was now in the valley of that bit down there. So rather than being where it is, it becomes in the valley here. If I want to find the PSD of response, we just simple equation. We take the PSD of input and we multiply it by the square of the frequency response function. We square the frequency response because the PSD is squared. Remember, it's mean squared units. So if we square that and multiply the two together, this is my response. And if I calculate the area under that, square root it, that's giving me that the RMS response under this wind is 6.8 millimeters RMS of displacement. So very, very moderate displacement in this case. Okay, so we've done a very simple look through how structures respond dynamically, and we've looked at how we can characterize the loading environment through power spectral density, and we've seen how, through a very simple equation, we can take a PSD of load, multiply it by the square of the frequency response to predict what the PSD of the response is going to be at the end. Now, this is a very simple case. I've not included effectively transient dynamics. This is all steady state in this case. We haven't really got time to go into the transients approach, but hopefully you've seen how we can do it for a very simple random steady state approach. Just before we finish, what I'd like to talk about, though, is multi-degree of freedom structures. So these are the ones like that multi-story tower block, which has got effectively multiple modes. So we're going to talk about modal frequencies, mode shapes, nodes and antinodes. We're going to talk about how we can calculate the frequency response function for multimodal structures. I also introduced this concept of anti-resonance, and we'll look at how we can use things like experimental modal analysis or operational modal analysis to estimate what the damping is. So first of all, I'm going to use the same example we've been using all along. So I'm going to use that wind turbine, again with fictitious stiffnesses and masses. This time, rather than having a simple structure, I'm going to distribute the tower mass as well. So I've got my nacelle mass of 38 tons. I've also got 5 tons of tower at each of these lump mass points. Okay, I'm using the turbine just so we can compare results with what we saw earlier. We could use the multi-story tower block or anything else to illustrate it. Now, when we go for multiple modes, we need to use matrices. So very often, unless you've got a nice maths package available, and within Glyphworks, obviously, we use that IMSL libraries that ship with it and Python to build this. That gives you then similar capabilities then to MATLAB. Of course, you can use MATLAB and MathCAD if you wanted to. Or if you've got very complex structures, then kinematic or rigid body modeling tools can be used as well. But what we need is a matrix solution. So here we've got our tower is built up of beam elements. The beam elements I'm doing are very simple in this case. I'm just using 4 degree of freedom beam elements because it's a simple 2D shape. I've got shear and moment transfer. And if anyone wants to try them out, here are the numbers for the stiffness matrix that you can see, and here are the numbers for the mass matrix. And again, I'm just assuming a very simple mass matrix. It's what we call a lumped mass model. So we're just assuming that there's a mass at each point. And because we've got a bending moment as well as shear transfer, then it needs to have effectively a rotational mass as well. And I'm just assuming they're unity for this case, which will give us a good separation between them. Okay, beyond words then. Natural frequencies. We saw earlier that we can calculate the natural frequency in hertz of a simple single degree of freedom system by taking the square root of its stiffness over its mass. Now, the fact we've moved into finite elements doesn't change it. It's still a simple approach. You can see what it is just down here. This time, the mass and the stiffness is a matrix. It's not just a single number. But K over M can be done in matrix notation as m to the minus 1 dot k. So we're using effectively matrix algebra to do that simple equation. And here I'm only interested in the eigenvalues. So if I were to run that through the IMSL libraries, I can actually calculate a vector of frequencies. The top 4 frequencies are all very high. They're separated because they're the rotational modes. The bottom frequencies are the ones I'm interested in. These are the forward-backward modes. And we can see that the lowest mode here is 0.67. And remember from our earlier calculations, the simple hand calcs, it was 0.625. The reason this is different is I've actually separated the tower masses in this case so that they're more effectively modelled. So that's made a slight change, but it's not a dramatic change to it. The key thing, though, is to understand just because we've moved from single numbers to matrices, you know, we're not introducing huge complexity. We can handle that. You'll also see that a lot of people, when you get talking to people, they may talk about things called eigenfrequencies. Eigenfrequencies are natural frequencies, are the same as resonant frequencies. It's just a different terminology for the same thing. And it's called an eigenfrequency because they've used the eigenvalues solution to find it. If I were to substitute, rather than doing the eigenvalues of the m to the minus 1 dot k, if I choose the eigenvectors, then for each of the frequencies, I get a vector. This is actually the mode shape. So we can see here, those last 4, the dominant frequencies here, we can see the shape of those. And if I were to plot those, this gives us those characteristic mode shapes. So the eigenvalue tells us the frequency at which the motion is going to occur. The eigenvector tells us the shape of it. And we can see for this simple tower at 0.67 Hertz, it's a simple for a sway type mode. As we move into mode 2 at 7.9 Hertz now, we can see how the mode's changing, mode 3 and mode 4 and so on. And we saw in total there were 8 modes because the other 4 modes are to do with the rotation of those points. There's a few other things that we know here. If you've got a point where the structure doesn't move, we call that a node. So that is a point of 0 displacement. And a point with maximum displacement we call antinodes. Now this causes problems when we talk about dynamics, especially with finite element people who all think that nodes are structural points on their finite element mesh. And that's why sometimes when we talk about dynamics, people will refer to the FE nodes as points, and that helps us to distinguish them between dynamic nodes, which are actually points of 0 displacement. It's also important, as we'll see later, that when we're doing experimental modal analysis using hammer tests, if we were measuring the response at a node point on the structure, it would, by definition, not pick up a particular frequency. And that's why one of the reasons why we always choose lots of points along a structure, because we know that nodes are going to exist. And at certain frequencies, we will miss those characteristic points. So how do we calculate the frequency response then of a multi-degree of freedom system? Well, again, just beyond words, we've got a few more maths. And we saw in a simple single degree of freedom system that the frequency response function is simply 1 over minus m omega squared plus k. Just because we're in matrices doesn't make it much more difficult. All we do now is we take the mass matrix, the stiffness matrix, we invert them to create what is now our frequency response function. And rather than there being just one natural frequency, we'll now see in this region from 0 to 50 Hertz, we'll see 4 natural frequencies. If we look at the bottom, at the bottom plot there, we can see the displacement there. We can see the first mode coming in at 0.67 Hertz. We can see the second one coming in there at about 7.9 Hertz, and so on. As we move up, say, so if we were to stick an accelerometer at 0.4, we get a time history, we can calculate its PSD. This is the sort of shape that we would see. If we move up to 0.3 though, you'll notice that all the peaks are at the same point, but you'll notice that there's now what we call an anti-resonance coming in. And when we get to 0.2, you'll see that now we've spotted 2 anti-resonances. You'll also see that whereas all the peaks, the resonant frequencies, are fixed, they're all in a line, the anti-resonances move around between them. So what is an anti-resonance? Well, if you think about it, a resonance occurs when the forcing function is in phase with the loads. An anti-resonance occurs when it's the opposite way around. And whereas resonances are always fixed in frequency, the anti-resonances will move depending on where you're measuring it. So again, when we're doing modal characterization and testing, be aware that you will see these anti-resonances. By the time we get to 0.1 at the top, you'll actually see this strange shape. What we've got now is anti-resonance and resonance coinciding with one another, which is why we get this big change. And if you looked, I've not done this in this because we've only had an hour really, if we'd have looked at phase plots, then what you'll find is that every resonance occurs when we get a change in phase from 180 to minus 180 degrees, and an anti-resonance is when it goes the other way around. So for every resonance, there must be an anti-resonance at some point that comes in between them. But they're not nearly as stable in their frequency position. Now, that plot showed undamped response. The equation had no damping in it. How do we find out what damping is? Well, we could do it analytically. If we knew what the damping was of each of the elements, so maybe structural type damping or the friction, We could build it into the finite element model if you wanted to, in each element. But a much better way of doing it is to measure damping through experimental techniques. And the two common techniques here are experimental modal analysis and operational modal analysis. So what's experimental modal analysis? Well, in a nutshell, we take our structure and we hit it with a hammer. The hammer blow is actually a very light, short duration. It's an impulse. And that short duration event will excite all of the modes at all frequencies simultaneously with almost a white noise. That it means that if we hit it with a hammer, we can measure at various locations on the structure and we can measure the response to it. And from that, we can calculate the frequency response function. So this enables us then not only to see where the natural frequencies are, but also to look at what the damping ratios are for each of those natural frequencies. Now, the other technique, operational modal analysis, is slightly different. With very large structures, it can sometimes be difficult with a hammer to get enough energy in there to actually deliver a result. So if we're measuring some turbines like this, they're physically very big. Hammers tend to be fairly small. Bridges are another problem. It's very hard to excite all of the modes of a bridge simply by hitting it with a hammer. In that case, we're better off just using the vibration of the structure as a whole. So the difference between the two is, in operational modal analysis, we use natural occurring event to effectively excite the structure. Experimental modal analysis, we excite the structure usually with a tuned hammer. And the other thing is, with the hammer, you'll tend to instrument one accelerometer, probably at this one near the top of the tower, and you'll hit various points with the hammer, and you'll calculate the different things as effectively the damping based on the net results of those. With operational modal analysis, you tend to measure all of the responses simultaneously to the same force, but we will get similar results. And I think the thing from this is, this isn't really a webinar on modal analysis. That is one huge subject. What I would like to get out, though, is that it is really important to do the modal analysis. Very often as engineers, we're forced to guess the damping. And people often say, oh, let's just assume it's 5%. But if you're exciting a structure near its natural frequency, damping is the only thing which controls it. And the number of times we've looked at vibration-induced fatigue, and we've found that it's got a fatigue life of, say, 20 seconds, and it's purely down to the fact someone guessed the damping ratio. It's very quick and very easy to do a modal analysis test, and it will improve your results in stress and fatigue astronomically if you did it. So really, I would try and insist that you do this for real calculations, especially where strength and fatigue is concerned. Once we've done that, we can actually look at the effect of damping. So the red curves here, these are our frequency transfer functions or frequency response functions for the undamped. And of course, what we're seeing there in blue is the damped. And the nice thing to notice is when we look at the damped response, that we can actually see it affects not just the resonances, but the anti-resonances too. So just to finish off then, if we were to do this with our wind turbine problem, we saw earlier on that actually the wind turbine, I've not managed to quite detune the tower as much as I could. I need to taper the section really to do that. So I could have done it better if I wanted to, and no doubt the turbine companies do. We see in this case that the first mode natural frequency is about 0.67 hertz. So that's well within the wind loading. The second mode natural frequency in this case was 7.9 hertz. Actually, at 7 hertz, there's very little load coming in through the turbulent wind. Wind turbulence tends to be a fairly broadband but low frequency phenomenon. So in this case, we're not too worried about additional modes we can design our wind turbine tower as a simple single degree of freedom structure. Unfortunately, life's not always so simple with other structures. So the turbine blades, for instance, they will have quite a lot of modes coming in, torsion modes as well as bending modes coming in, and they will probably be excited as well. The Tacoma Narrows suspension bridge also has lots of modes coming in, so it's not always so simple. So just to finish off then, what have we covered? So we've split it down into three sections. First of all, we've looked at the structural response, and in particular, we've looked at the dynamic equilibrium, the equation of motion, and we've seen how we can solve the natural frequency. We've also looked at the same equation and see how we can solve it slightly differently to calculate the frequency response function. From that, we've seen how damping affects that critical area in the vicinity of the natural frequency. Above 1/3 the natural frequency is solely controlled really by damping. And we've covered a bit about what we mean by quasi-static response. And we've also looked at just one plot which illustrates the effect of linear and nonlinear structures. We then went on to look at loading. So if we want to design a structure to avoid key natural frequencies, we need to know what the loading are so we can detune the structure. And we introduced the power spectral density for that. And we also looked at how the power spectral density and frequency response functions can be used so that within certain cases, that of random loads with steady state conditions, we can estimate the response spectrum. And then in the last section, we very quickly looked at really about using matrices, and by the time you do this, you'll be using finite element and rigid body analysis tools usually, to plot the frequency response functions, to look at multimodal frequencies, mode shapes. We've looked at nodes and antinodes, anti-resonance, and we took a very quick look at experimental modal analysis and operational modal analysis as techniques which we recommend to use in order to work out what damping values. If anyone wants to find out any more, then I have a paper which I just need to finish off, which can accompany this webinar if you're interested. And also, it might be worth you seeing the manual for some of the tools in GlyphWorks for this. So the frequency response analysis tool is used for getting the frequency response function. The frequency spectrum tool gives you the PSD. The joint time frequency analysis tool helps us to see how the PSD changes with time. And if we've got an increasing load, for instance, going in, it will enable us to start to see nonlinearities within the response. And waterfall analysis, very similar to short time frequency, but this one is usually a plot of PSD versus rotation speed for things like generator or engine run-up tests. So these are things, some of the tools within GlyphWorks that will help you look at the things we've done. Okay,